In 2017, a single research paper titled "Attention is All You Need" was published. Within a few years, the math inside this document spawned a multi-billion-dollar industry and the current generation of frontier AI models. This diagram shows the original architecture, divided into two distinct halves, an encoder block and a decoder block. Initially designed for translation, text feeds into the encoder, passes across a central bridge, and the decoder outputs translated text. While the encoder was necessary to process a separate input language as context, engineers realized that for generating novel text, the only context required is the sequence of words already produced by the model itself. This realization led to the removal of the encoder block entirely. Modern frontier models shifted the decoder to the center, creating a streamlined decoder-only architecture. To understand how modern large language models process data and generate text, we need to reverse engineer this surviving half. We have to look inside the decoder. Generating context-aware text one word at a time across billions of parameters requires a highly specific mathematical anatomy, a structure that allows the model to map complex language patterns without losing track of the sequence. The first critical component inside this block is causal multi-head self-attention. Self-attention is the mechanism that calculates semantic dependencies. It examines tokens within a single text sequence and determines how heavily they relate to one another. The multi-head extension runs several of these attention calculations in parallel. Instead of finding just one connection, it maps multiple relationships at once, like subject-verb agreement or pronoun references. But training an autoregressive model introduces a strict constraint. The system must learn to predict the next token based entirely on past tokens, without accessing future ones. Look at this matrix mapping, "the sky is blue." Standard attention lets the model see future words. To fix this, a mathematical mask drops over the upper triangular portion, severing connections to the future. Now, the model relies solely on preceding tokens during training. The underlying math driving this mechanism is known as scaled dot product attention. Modern models optimize this calculation further using variants like grouped query attention in Meta's Llama or multi-head latent attention in DeepSeek. By implementing this mask, the architecture enforces a hard mathematical limit. It forces the network to learn genuine predictive logic, rather than copying data it shouldn't have access to. While the attention mechanism maps the horizontal relationships between different tokens in a sequence, the model also needs to build deeper individual representations of those tokens. This is handled by the second component, the feed-forward network. As this diagram illustrates, when a data vector passes into these fully connected layers, it expands in dimensionality. This expansion increases the model's representational capacity, allowing it to process more complex information about each token. Within this widened space, activation functions like swigglue are applied, capturing complex internal patterns about that specific token. Once processed, the high-dimensional data projects back down to its original width, compressing the learned information before passing to the next layer. Attention extracts context from the surrounding sequence, and the feed-forward network drives vertically down into the complex meaning of the individual word. Passing massive data arrays sequentially through hundreds of these attention and feed-forward blocks creates friction. Over deep networks, gradients degrade, and the math becomes unstable during training. To maintain signal integrity, engineers borrowed a technique from image recognition called residual or skip connections. This structural schematic shows the mechanics. The main data path splits. The input bypasses the processing blocks entirely and is added directly to the output, creating an unimpeded route for gradients to flow. The fourth and final component manages the scale of those flowing numbers, layer normalization. Layer normalization normalizes a token's feature vector to a zero mean and unit variance. Originally applied after sublayers, today's standard is the pre-LayerNorm pattern. As highlighted here, normalization now occurs right before data enters the attention and feed-forward components. Cutting-edge models often streamline this further by using RMS norm with pre-normalization, which maintains stability while drastically cutting computational cost. Without these structural stabilizers, the residual bypasses, and the normalization layers, the sheer depth of a modern frontier model would cause the math to collapse during training. Here is the final assembly. The attention, feed-forward network, pre-LayerNorm, and residual components snap together into a single cohesive unit, the decoder block. A modern large language model is simply a stack of these exact blocks, duplicated vertically dozens of times. To run end-to-end inference, an input sequence is first broken down into tokens by the tokenizer. Those tokens are converted into input embeddings, dense numerical representations that contain both the meaning of the word and its exact position in a sequence. This data stream enters the bottom of the stack, rippling upward and being sequentially refined by every single decoder block. Upon exiting the top of the transformer stack, the final tokens vector undergoes one last layer normalization. This graphic shows that normalized output vector passing through a linear layer. It instantly expands into a massive, dense bar chart of raw scores, known as logits. These raw logits are then converted mathematically into an actionable probability distribution, assigning a percentage likelihood to every possible next word in the model's vocabulary. The system uses specific decoding strategies to select a single token from these probabilities. That chosen token becomes the next generated word. The input sequence includes this new word, and the autoregressive loop fires again. Frontier AI functions as a continuous cycle of predicting the next token.